the introduction of the LBSP seminar, which I'm sharing today. Jean-François Ripoll from CEA. Welcome, everybody. I'm sharing instead of Sasha Ukorski, who's at EDU today and unable to do it. So it's a pleasure to have today two speakers on the subject of machine learning. Professor Jacob Bortnik will be speaking first about magnetospheric prediction with machine learning. And then Enrico Camporeale from NOAA will follow. It's a tandem talk, as you know now the format. And Enrico will be speaking about Fokker-Planck simulation combined with machine learning. So it's a general hour on machine learning techniques who are just booming in the field and with highly promising results. So let's start with Jacob Bortnik. If you can share your screen, Jacob, and I'll let you talk.
All right. Thank you very much, Jean-François. I will try and do this. Okay. Can you guys all see my screen well?
Yes.
Okay, great. Let me do that. Okay. Oh gosh, it's showing up badly on my screen. If I do this, does that show up?
If you do that, we see actually your notes on the side.
I see. Okay.
And now we don't.
Okay, sounds good. Thank you very much. Sorry for the technical difficulties. So, as Jean-François said, today I'll be speaking about inner magnetospheric environment reconstruction and explainability. And I originally wanted to, include a little bit of imbalanced regression, which is the topic we've been working on lately, which I think is very interesting and important. I may or may not get there in my allotted 25 to 30 minutes. So I just put it there in brackets. I also want to acknowledge that the majority of this work was done by my graduate student, Donglai Ma. And some of the former work was done by Xiangning Chu, who's a close collaborator and a former postdoc at UCLA. So I want to thank them both, as well as all the other people that have contributed data or ideas or discussion listed below. So without further ado, this crowd probably needs no introduction to the radiation belts. So I'll keep my introductory slide to basically this just one very short summary slide. As we all very likely know, the radiation belts consist of a population of magnetically trapped energetic electrons, and by energetic I mean hundreds of keV, where magnetic drifts dominate the particle motion, up to several MeV. This is a population that experiences three periodic motion, a very fast gyration about the magnetic field line with frequencies at kilohertz, bounce motion up and down the field line to the northern and southern mirror points, and a slow drift around the Earth on a time scale of several hours, which translates to frequencies on the range of millihertz. So why do we care about the radiation belts? Well, they are scientifically interesting. There are a range of space plasma physics that goes on over a variety of scales. There are natural and multiple wave-driven acceleration and loss processes. There's transport, redistribution. So there are all kinds of very interesting things that work in a system that then communicates to different energies of particles, different species sometimes. It's also a space weather hazard for spacecraft. There are a variety of effects that the radiation belts can impose onto spacecraft. So there is societal importance. And so reconstruction and forecast becomes important, as well as understanding what it is that actually goes on in the radiation belts. And the cartoon sort of in the top right here illustrates graphically what a single charged particle might do. You can see the radiation belts are shown in color. This is the population of these energetic electrons. And here schematically, whoops, no, why it keeps doing that? And schematically, here is a plot from one of Dan Baker's papers in 2017 showing Van Allen probes data from A and B over a number of years. L-shell is shown on the y-axis, time is shown on the x-axis. And we can see right away that the radiation belts vary, they intensify, they drop out, they do all kinds of interesting and complex dynamics. the way we typically model radiation belt dynamics is with the Fokker-Planck diffusion equation. And this is a physics-based equation, although if you look carefully, the equation itself takes in parameterized plasma wave properties. And so these diffusion coefficients, even though they're calculated based on first principles, what goes into them to drive them is actually data, essentially. It's data that represents distributions of particles. There are also initial conditions that are driven by data, time-varying boundary conditions. And so, okay, so if you put a red rectangle around this whole equation, it can essentially be thought of as a transformation. So all kinds of data goes into it, and what comes out of it is just the radiation belt temporal variation, the phase space density at a single point. And of course, you can repeat this over time and over multiple spatial locations, but it's essentially a transformation that takes in data and spits out phase space density variation. Don't get me wrong, the Fokker-Planck equation is extremely useful. It's valuable. We use it a lot of times. It's the primary tool, if not the only tool, that's used to represent the global variability of the radiation belts, but it's not necessarily the optimal transformation of data to phase space density. You could, for example, have times when a diffusive framework is not the correct one. There could be terms that are missing, and they could be missing sometimes and not at other times. And in fact, Enrico is going to speak in the second half of the seminar about how you might go about discovering such terms. Now, what I will talk about is finding a most general transformation of data to phase space density variation or flux variation. And for this, we're going to use machine learning. So specifically, I'm going to talk about a machine learning model that we've developed here at UCLA. This is called the ORIENT model. ORIENT stands for Outer Radiation Belt Electron Neural Network Model. There is one neural network model for every energy channel that we train on. And there are two basic versions of this model. There's a medium energy version, which we call ORIENT-M. And this is trained on predominantly Van Allen probes MAG-ICE data. So it spans energies of 50 keV to 1 MeV. And the ORIENT-R, which I've spoken about previously, I won't repeat now, but this is trained on REPT data and goes from about 1.5 to 20 MeV. These two models are described by separate papers, one by Xiangyi Chu in 21 and one by Donglai Ma in 22. And what I'm showing here is a plot from one of Donglai's paper that shows how the model performs. And so in the top, you see the drivers to this model. These are the DSD index or SIMH index. This is the AE or AL as we've started using. These are solar wind parameters, V solar wind and P solar wind. And we just use time series of these input parameters. And just based on these time series, there's no actual satellite data that acts as a boundary condition here. We reproduce the radiation belts. Here are observations from RBSB A and B this is 597 keV electron fluxes, about 600 keV. Let's see, this is the observation. This is the prediction from our model. These are out of sample predictions. And so you can see that the machine learning model, the ORIENT-M model, captures the dynamics extremely well along the orbit. You can also do a line plot of observation to the model, and you can see that there are, of course, times when the model and observation disagree, such as these, very low times when observations goes low. But on the whole, the model does an excellent job of reproducing the general dynamics and behavior of the radiation belts. So just to give you a little bit more detail, we trained on Van Allen probes data over the entire mission. We have about 7 million points in total, above L of 2.6. For the ORIENT-M model, even though the energy we choose is fairly arbitrary, we focused on 4 key energies: 50 keV, which represents source electrons, 200 for seed electrons, 600 for the lowest radiation belt energies, and the 1 MeV or 900 keV, which represents kind of the output of this whole process. And the features, as I've said, satellite location, geomagnetic indices, specifically DST and AE, and solar wind parameters, and we take time series of those. Just a slide on model optimization and error analysis. I won't belabor this point, but just to say that we spent a great deal of time testing and validating our models. This is just an example of test data set. For example, what I mean is out of sample data set. So here's the 50 kV, 200, 600, and 900 kV. And you can see that the mean squared error is low, and the variance that we capture of the variability is sort of in the 80 to 90% range. This is all data that the model has not seen. It's completely out of sample. The way we make sure we don't have any data leakage is we divide our data into 2-day chunks so that there's no kind of crosstalk between these data chunks. We also don't just train one model, we actually train thousands of models, and we experiment with all kinds of things. Here, for example, is the look-back window, the length of the look-back window in days for the various energies. And you can see right away that for something like 900 keV, when you take a look-back period of 10 to 15 to 20 days, the optimal point lies somewhere around here, sort of the 15 to 20 day range. This is the high energies, and they need a lot of time history of what happened previously. If you look at 50 keV, for instance, we need a much shorter time history. We only need several days to reach the lowest mean squared error, and each one of these vertical bars represents a number of models that we kind of randomly permute so we can get some kind of a distribution of the error. So there are thousands of models that go into this, and we believe that we reach essentially the optimal point of what we can do. Okay, so we have a model that we're happy with. Here are some examples of the output. This is 50 keV data. You can take a single event, single storm, and look at different snapshots of it, as shown on the left-hand side here. So A through E are different snapshots. The different rows here represent different energies. And as you can see, as the storm goes on, you get this intensification, particles get trapped. The behavior is different for different energies. There are asymmetries that develop in the tens of keV particles that tend to go away by the time you reach several hundreds of keV particles. So the model behaves very reasonably. It reconstructs what you should see globally based on individual points. And this is only based on solar wind parameters and geomagnetic indices. So wherever you have those inputs, you're now able to recreate the dynamics of the radiation belts across a range of energies. Okay, so this is the prelude, essentially, to my talk. Whoops. Okay. Now let me get into the main topic. So once we have a trained and validated model, we can then start to ask, how's the model actually making its decisions? What is it using? What is it in the features that makes it behave in the way that it does? And so without going into too much detail, let me tell you in very broad terms about this very interesting method called the SHAP method. SHAP stands for Shapely Additive Explanations. This came out of a paper in 1953 by Lloyd Shapley, who happened to be just down the hall here at UCLA. Won the Nobel Prize in economics for his method, and adapted to machine learning quite recently by Scott Lundberg and Soon-Ju Lee, I believe is the name. And so the idea is basically, you have your data and you have your machine learning model, as I've shown in the previous slide, which makes a prediction. The machine learning model typically tends to be very complex, and so you don't have a lot of visibility into it and how it's making its decisions. So how do you come up with a method that is able to explain or interpret what the model is doing? And this is this whole idea that Lundberg and Lee came up with by adapting the Shapley method. So the idea is you create a surrogate model, what we call G of Z dash, which is essentially a linear combination of its features. So Z sub I dashed are the features that go into this surrogate model. And this is the explanation model. And so the Shapley values are these phi sub i's, which tell you how each of the features is weighted locally. So this is where a single point, a single prediction that your model is making. How does this method differ, and why would Lloyd Shapley get a Nobel Prize for it? Well, it's because making a linear model can be relatively easy, but making sure that it's fair is very, very hard. And so the basic idea that Shapley came up with is from game theory, and it's the idea of fair attribution. So, so in a coalition, for example, a coalition of 8 people, how do you figure out what the contribution is of this bloke over here? Let's call him Bob. And so what you do is you create coalitions with and without Bob. And so they're going to be a very, very large number, kind of a factorial order number. If you have 8 people on a coalition, right, that they create some kind of a product and they generate $1 million for it, how do you know what portion of that $1 million is attributable to Bob? And so you create coalitions with and without Bob. So the simplest one is to have all 7 members that contribute, and then you include Bob and you see what the model predicts, and you exclude Bob, or just give an average value for Bob, and see what the marginal contribution, how much extra Bob contributed. The problem is that there can be very many such coalitions. There can be coalitions of 2 people, 4 people, 5 people. And so the idea is that you create coalitions with and without Bob, or permute them across all possible coalitions, and then basically average across all of these marginal contributions, and that gives you the value phi sub I. Okay, so that is in a nutshell what the Shapley value is. Lundberg and Lee adapted it to machine learning and came up with a method that wouldn't necessarily have to brute force all the factorial combinations, because even with something like a few thousand features, it becomes an astronomically large number that cannot be handled by modern computers. Okay, so let me show you how this works in our case. So here are the features that go into our machine learning model. This is the Orient-N model. We have a black box, that's the neural net, and it spits out a flux time series at some given L shell, and we do this for all L shells at some t. Now, this is t sub 0, and over here, we're interested in saying what of these features contributed to the decision of the model to make the flux, this value right over here. So you take the training set and you compute the surrogate model, compute the SHAP values for this particular point, and you see that AL contributed positively to some degree, some H contributed negatively to some degree, and when you sum all of these together, you get back to this value. This is why SHAP is an additive explanation model. You can do this across all L shell, and this is essentially what we've done here. So this is just a reminder. And so what you see is the different features at time t0, what contributed to this flux at different L shells is shown by the color here. And so you can see that AL contributed positively, that's the red color, and SimH contributed negatively at this range of L shells and positively here. And I'm sorry, I had my my diagram unfortunately placed over there. Okay, so now what we can do is we can take a typical event shown over here. This is our model results now. This is data. These are our features, and we can step through it in sequence. So A, B, C, D are different time snapshots, and we can see that the model at time A took these features and basically they did not contribute very much. The color bar shows the Shapley values, and you can see that there's a little bit of positive contribution from AL way back over here at this distant time, but essentially the model just gives a background value. As soon as you go to B, look at what happens. The flux drops out. What makes it drop out? It is the combination of pressure in the solar wind becoming high, so you can think about magnetopole shadowing, and DST or SimH going very low. So you can think about possibly the DST effect inflating, your outer radiation belt in combination with P solar wind. So these two values at L shells of 4 and greater are causing the flux to all be lost out of this region. And as you can see, the AL drops, the sort of substorm activity, is kind of mildly trying to do some acceleration. Let's go to times C, the fast acceleration time. You can see that SimH the low SMH value is still inflating the magnetosphere. It is still causing loss, but only at very sort of local time steps. The acceleration is predominantly caused by this series of AL values dropping lower and lower. Let me see how I'm doing on time. I'm almost out of time. Okay, and then in time D, the acceleration essentially slows down, but it is still controlled now, deeper back in history by the sequence of AL values, as well as at low L shells, this is L of about 2 or 3, by the SMH drop. So you can maybe think about sort of a reverse DST effect on the inner portions of the ring current. I hope that's all clear, because now we're simply going to use this Shapley explanation value in a couple of different contexts. We can now go to non-storm time acceleration. So here's some H did not drop below -50. This is a non-storm time period. This is one of the gem storms. And so how do you interpret such an event? So the event here, there's no major loss. There's no kind of a big deep blue period, but there are sequences of deep red, meaning that the AL index or substorm activity basically contributed to sort of this piecewise acceleration whenever it goes low. You can think about this representing substorm injections, kind of a short-lived localized acceleration process, and then kind of repeating this every time there is a substorm going off. So comparison between storm time and non-storm time acceleration. What about an acceleration event versus a loss event? So here we show two different events that have been that we applied the SHAP method to, one in March of 2013, one in September of 2014. The outcome of the storm is acceleration on the left side, loss on the right side. What is the difference in the feature attribution in this case? Well, here we see that there's relatively mild loss coming from DST effect, but a great deal of acceleration coming from intense substorm activity as well as a lower DST value. So you have predominantly rate and predominantly acceleration. On the right-hand side, you still see acceleration. AL is still trying to accelerate particles, but this is being swamped or overwhelmed by the solar wind pressure. And so as soon as it goes much above 10 nanotesla, you get this deep blue period, which wipes out the radiation belts in the outer portions above L of 4. Okay, so the radiation belts never recover. We can do this in a superposed epoch analysis fashion, and here we've simply mirrored what has been done by Katsabrias et al. In a 2019 paper. The paper did this in a superposed epoch analysis way, and here we've reproduced a superposed epoch analysis. We built a median model, as well as a lower and upper quintile, 20% of the values. And we've taken these exact same storms, 20 enhancement events, 8 depletion events, and we've applied the SHAP method, and we've superposed basically all the SHAP values together. And so we've stepped through time in these events. This is 5 hours, 24 hours, and 48 hours after the event. This is during the dropout, and so you can see again that in a superposed epoch way, it's the pressure of the solar wind together with the DST effect that causes the dropout just for a short time, and then followed by an acceleration period, which is dominated by a series of AL dips. Okay, and this continues through to sort of the 48-hour time frame. So now we have a way to peer under the hood of a superposed epoch analysis with the SHAP explainability method. Just a quick thing for fun. You can see that there's a sequence of AL values over here, and you might think, well, maybe it's just the amount of substorm activity that controls how high my fluxes are going to go post dropout. And indeed, we've integrated the AL value for 48 hours following the dropout and shown the results here. So the integral of AL for 48 hours, correlates very well with the post-storm fluxes. So our conclusion is, which I don't think is entirely new, is that it's the accumulated substorm activity post-dropout that controls the final intensity of the radiation belt fluxes. Okay, we can do the same for the depletion storms. Is it my time, Jean-Francois? You're muted. Okay, I'll try and wrap up quickly. So we can do the same exercise with the Katsavriyas depletion storms. Here again is the traditional superposed epoch analysis, a median machine learning model, and 2 quintile models. And if you do the superposed epoch analysis, you can see that these are indeed lost storms. They are being dominated by a combination of P solar wind, the velocity, and the DST effect. And there is just not enough AL activity or substorm activity post dropout to recover back to pre-storm values. And so this is, we believe, at the heart of what controls depletion versus enhancement. Okay, I'll say just 2 quick words because I have 4 minutes remaining if you don't ask any questions about imbalanced regression. So these are going to be my last 2 slides. Typically in space physics or physical science problems, we have a data set, and the thing in the data set that we care the most about is kind of like the very, very small part of the tail of the distribution. So this is from a paper that's currently under review by Xiangling Chu. It shows you lower band chorus distributions. Look at this one, for instance. This is, on the x-axis is shown the intensity of all chorus waves observed in the lower band on Van Allen probes. And this is just a sample number. And you can see that when we get to about 100 picotesla and above, these are the waves that cause most of the dynamics in the radiation belts. They're also the kind of extreme small, tiny tail of the distribution, right? This is what we care about, and yet it's the minority. And so when we train a traditional machine learning model to reproduce chorus waves in the way that I've shown you, we get something like what is shown in this panel, panel D. This is the time series for a particular time. It shows you 2 different kinds of machine learning models. These are the input parameters. This is the measured B wave. This is the traditional B wave model. And what you can see with this red dashed line is a traditional regression model, the neural network model, tries to regress its values towards the mean, hence the name. All right. So this kind of model is actually quite deficient for our purposes. How do we fix this? Well, we've come up with a solution which is called imbalanced regression. And at the heart of it is that we weigh the loss function for extreme values much more highly than the bulk of the distribution, so that the loss function starts to focus on the extreme values. This is what we call an imbalanced regression problem. And here's a model trained with this kind of jimmied loss function. And as you can see now, it starts to reproduce much more realistic values. Here's the imbalanced regression model B wave. It now gets into the hundreds of picotesla values, whereas the traditional neural network model does not. With this imbalanced regression model, this is my last slide, we can start to get distributions of chorus waves. Here's just a time sequence through a standard storm with a plasma pulse superimposed. During the heart of the storm, we see a lot of low band chorus activity right over here. And of course, this is a 3D model. And so we can examine the meridional distribution of the chorus waves at any time. And so this is what it looks like at different MLT values. You can see this characteristic day-side pattern of chorus waves that tends to be very weak around the equator and grow as it propagates away from the equator. So I think I'm at time. Let me summarize. We've developed this Orient machine learning model, which comes in 2 flavors, the M and the R, the medium and the relativistic. And what the focus of the talk was today was on the interpretation of this model. Once you have a very good representative model, you can start to poke it and explore it. We time step through individual events. We looked at storm time versus non-storm time. We compared enhancement versus depletion individual storm events, as well as superposed epoch analysis. And so you can really start to dive under the hood and understand what is causing the different dynamics of the radiation belts. Finally, I spoke about that. I only had a little bit of time at the end to talk about imbalanced regression of lower band chorus waves. This is important when you're dealing with a highly imbalanced data set, as we typically do. So I think I'll stop right there and hand it over to Enrico.
Thank you very much, Jacob, for being right in time. It's a very hard exercise, I know. I didn't see any question in the chat, but if I may, I would like to ask you a quick one, real quick. The SHAP criteria seems great to investigate the role of each index as you show. And in your model, I believe there are 4 indices. And I was wondering, because I know you're very interested in the plasma sphere and the plasma density, working on that for years. And that's going to be important for the loss, for instance, in the radiation belt. So how do you see that parameters entering the picture, and can you use the SHAP criteria to add more indices or parameters or physical quantities that would be relevant, maybe chorus power to try to get more insights and better parameterization of the prediction?
Yeah, really great question. So the SHAP value is a lot of its use is for feature selection. So you throw in a whole bunch of different inputs, and then you back it out with a SHAP and see what's actually important at what times. So the density is very, very important. In fact, what I didn't say is under the hood in the Chorus imbalanced regression model is we've used our plasmaspheric density neural net model as a density input to the Chorus. It actually provides much better predictions because the model knows, oh, you're in a low density region, you're in a high field region, and so on. And so I think there's much value to be gained out of a synergy of models, especially density, which tends to drive so many functions that go on top of it. So yeah, thank you very much.
Okay, so we will follow your work with interest as you go on. Thank you very much. Let's move on to Enrico Camporeale, who's going to continue the talk. Enrico, if you can share your screen. Thanks a lot, Jacob.
Thank you very much.
Okay, you're all good.
All right, thanks a lot. Well, thanks for the invitation. Thanks to Jacob for giving such a nice intro, so I don't have to spend too much time on the introductory stuff. So I'm going to talk about a work which has been recently published on JGR about data-driven discovery of Fokker-Planck equation using something called physics-informed neural networks. And these are the co-authors listed here. And I acknowledge the NASA support for this work. So let's just start right into it. So Jacob mentioned this 3D Fokker-Planck equation. In this work, we sort of step back and do and just focus on the 1D version of that Fokker-Planck equation, a much simpler scenario, which is the radial diffusion. So he mentioned these 3 adiabatic invariants. So this is a diffusion in the 3rd adiabatic invariant, which, as Jacob mentioned, is associated with a longer period, a longer time scale, and therefore it's actually the easiest, or it's the one to break. So this equation here is assumed to be valid for constant 1st and 2nd adiabatic invariants. And so the problem I'm going to focus on is what is known as inverse problem, and this is the inverse problem statement. So assuming that this is the equation we are happy with, or in a sense, we assume that this is the equation that describes our system, there are 2 free parameters here, DLL, the diffusion coefficient, and tau, the electron lifetime. So the question is, what is the optimal choice of those parameters that makes the results of the diffusion equation most consistent with data, assuming that, so in other words, this is why it's called the inverse problem. We assume we know the result F, and we use Banach-Lemprob's data for that, and we want to infer what are the optimal values for DLL and tau. And as you might know, solving an inverse problem is much harder than solving the forward model for many reasons, one of which is that the problem might be ill-posed, meaning that there's not a unique solution for that. Oh, I think I skipped one. So the typical approach for an inverse problem is a Bayesian approach. I'm not going to talk about that for sort of a lack of time. We did publish a work using that Bayesian approach. But here I'm going to focus on a machine learning approach, which is called physics-informed neural networks. This is the paper, the landmark paper. This number of citation might be outdated now. I believe now it's more than 3,000, but I sort of circled this number here just to give you a feeling of how important this method is rapidly becoming in the machine learning community in the applied math community in general, actually. And the first author is Mazar Raisi. So how does a physically informed neural network work in a nutshell? So the idea is the following, is that to include the partial differential equation we want to solve in the cost function. So I'm just gonna try to minimize my screen here. Second. Okay, so Jacob described neural networks. So the typical way of training a neural network is to have a cost function which has this term here on the right, it's the second term on the right hand side, where you basically want to minimize the difference or the error between the neural network output and observation. So you use data to sort of constrain the cost function, and at the end of the day, the neural network is just an optimization problem where you want to minimize this cost function. Again, F is the output of a neural network, F observation is your data. The pin idea is to, and the beauty of it, it's very simple, is to say, okay, on top of that, we also want a solution F that is the solution of a given partial differential equation. So basically, you plug in your partial differential equation in your cost function, and this is the square bracket here. And the trick under the hood, so the way this works is that it's thanks to something called automatic differentiation. So the idea is that all derivatives are computed exactly, unlike what you actually do in solving a forward problem like a partial differential equation, like numerical schemes. And this can be done because the output of a neural network is analytical and differentiable functions. So in other words, you can compute exactly all these d over dl and d over dt in any given time and space, any given collocation point in your domain. So the pin is both a gridless method to solve a PDE on a set of points, so to solve the forward problem, and it's also a way of estimating the coefficients of a PDE, so solving the inverse problem. So practically, how does this work for parameter estimation is the following, at least this is the way we used it. So assume that you have a PDE, again, this is a very general form, we have df over dt, f is the function of space and time, x and t, plus a nonlinear term h, which is a function of f, and some free parameters d and c. So what we do is to train, assuming you have two free parameters d and c, to train 3 different neural networks, sort of independently. Each of these neural network takes as an input only space and time. So you train these sort of scanning your domain. In our case, space is just a 1D variable, so it's a 2D domain, and you just plug in those numbers x and t in your network, and you train independently these 3 networks. The output of each is f, d, and c, and then those 3 numbers get sort of plugged in the loss function, which again is a sum of say mean square error, so a traditional loss function plus the residual of your partial differential equation. And by way of training these sort of, when you do the back propagation, what happens is that this 3 neural network gives you the optimal f, the optimal d, and the optimal c to solve this PDE. Well, to solve this PDE and also to match the data as best as possible. So there's a big caveat when we want to try using this technique for our radial diffusion, is that if we, again, starting from the first equation, which is the standard radial diffusion plus a loss term, if we allow DLL and tau to be too general, this becomes just too much ill-posed for an inverse problem, where it means that you can figure out that very quickly there are pardon me, there are infinite combinations of DLL and tau that actually give you the same result. In fact, you can think of any value for DLL, you plug those in, f is known from data, and you can actually solve explicitly for tau here. So for any value of DLL, there's a corresponding value of tau that solved the equation. So what we did is to sort of step back, and as Jacob mentioned, you can think of maybe more general equations or other mechanisms that are not captured by the diffusion equation. And we focus on a more general form of a Fokker-Planck equation, which is drift diffusion. So effectively what we did is to replace the F over tau term, which again is too general, to some sort of more constrained term, which is a drift advection term with a drift coefficient. So here, that's where our DLL and C coefficients now are our free parameters. Okay, as usual, when you try something new, you want to have some baseline models. I'm not going to spend too much time on this. This is kind of known in the literature. The Brautigan and Albert is possibly the most popular or most widely used model for radial diffusion. Then these are the two more recent papers we compare with. Also, you need some sort of definition of errors, and we actually use 3 different errors. These 2 on the top, the percentage symmetry accuracy and the symmetric sign percentage bias, are actually sort of slight modifications of metrics which have been proposed in a paper by Steve Morley. And then the one on the bottom is simply the relative error of the log of the phase space density. And we work in log space just because F ranges several orders of magnitude. So here, F will be the output of your neural network, and F hat will be your observations. And P50 here means just the median value, because what we really want, so F is function of space and time, L and T, but we really want to have just a single value for a given L. So basically, we just take the median over time. All right, so we used Van Allen probes data to train the physics-informed neural network. And what we did is, so we took 4 years of data at the given fixed value of mu and k, which are reported here on the bottom. And we sort of split kind of arbitrarily the set into the first 3 years for training and validation and the 4th year for testing. Okay, something to keep in mind whenever, and this was also sort of touched upon by Jacob, whenever you train a neural network, I mean, neural networks are sort of stochastic beasts, meaning that they very much depend on your initial conditions, and they tend to converge on local minima. So what you should always do, in a sense, when working with neural network, is to try an ensemble of that, just changing the initial weights. And that's what we've done. We trained 20 different physics-informed neural networks. And what is shown here on the top row is the diffusion coefficient, and on the bottom row are the corresponding drift coefficient for the best 5 solutions, where by best we mean that, you know, we plug in those numbers in the forward model, and those are the coefficients that gives you the best agreement with data. And we can see that, you know, the solutions are all different. I mean, the large scale structure, I would say, are very similar, but the fine scale structure might be different. Okay, this is not surprising then when we look at the results on the training set, because this has been used for actually optimizing the problem, or to find those coefficients. We find very low errors, epsilon as a function of L, which actually outperform all of other baseline models. Now, the crucial point is the following. Once you have made the assumption, and this is possibly the critical assumption, that this drift diffusion equation is the equation that describes your data. Now, this method, the physics-informed neural network, possibly is, I believe, I mean, as far as I know, is the only method that actually allows you, without parameterizing DLL and C, to give you what are the optimal values of these 2 coefficients as a function of space and time. And this is really all the information you need about the physics of interest, because all of the physics, in a sense, is embedded within this coefficient. So you can do then some kind of data mining, because this is all the information you need to actually understand what is going on. And this is what we have been doing. All of these details are in the paper. So the first thing is to do a statistical analysis of the coefficients. So how DLL and C change statistically as a function of L. And so here the orange line is the median, and there's a gray area, which is the area between the 25th and 75th percentile. And you can see, so this is how the log, as I said, we tend to work in log space. of DLL changes as a function of L, where we fix our boundary conditions at L equal 2 and 5.5. You can see there are clearly 3 different regimes of how this diffusion coefficient changes with L. And just for clarity here, I have superposed in yellow L to the power of 10, which is actually the parameterization used in Broughtingham and Albert. And you can see that this parameterization doesn't do it does quite well actually for small values of L, but maybe a larger power in DLL, L to the 20, will do better for larger values of L. And you can play the same game for C, where here the errors, especially at the outer boundary, are larger, but again, there are at least, the very least, 2 different regimes, which might actually have to do, so this kind of elbow here might have to do with the plasma pose location, which is something which is not hardly coded in the method. So basically the method sort of discovers by itself a statistical description of where the plasma pose is on average. Okay, another thing we can do once you have this information about the optimal values of DLL and C is a feature selection. So Jacob mentioned the SHAP method. This is a much simpler method to do feature selection or to rank different features, which is called backward elimination method. And it's based on it's very simple. So the whole idea is you train a generalized linear model. So you start selecting like 15 or 20 different features, and then you decide that your linear model is based on combination of those features, say up to 2nd order. So you end up starting with about 100 different features, combinations of those, and then you move backward, meaning that you start eliminating the ones which are less relevant to your model, that contribute the least. So the way to read those plots from left to right is, if you only have L as your feature, so you will have sort of a model based on a single parameter, you get R squared, a coefficient of determination, which is basically just the square of the linear coefficient, equal to 95%. So already only using L for DLL, you already get a correlation coefficient up to 95%. Then if you add the 2nd parameter, for this improves, and then a 3rd parameter up to a point where this kind of saturates. And the red dashed line here is the best you can get when you use all parameters. And you can play the same game for C. Something I emphasize here is KP, which is actually the key parameter which has been used in the literature to parameterize DLL and C, where this doesn't even appear in the first 10 for C. And I think it's number 6 in DLL. So one of the goals for further improvement of the or usage of the method is to parameterize DLL and C without using KP. So this is a kind of the pipeline of the whole parameter estimation. So you start assuming that the physics obeys a given equation, a Fokker-Planck equation. You run your pin, and this gives you the optimal coefficients as a function of space and time in your training set. Then you run a feature selection, and you understand how you can sort of describe those coefficients in terms of a few parameters. And then what we tried is to do a step forward to actually use this method for forecasting, and we train a different machine learning method that actually predicts DLL and C at any given time. And if you do that, then you can plug in this prediction of DLL and C in your forward model, and you can actually use this for prediction, as long as you have an estimate of the boundary conditions. And those are the results on the test set. I'm not going to spend too much time on this, but it just shows. So these are now this epsilon value, the relative error as a function of space and time as a heat map. These are on the top left is the result of this work. And then the other 3 panels are the other 3 different baselines. And you can see that this outperforms all of the 3 baseline models. And those are 2 sort of vertical cuts for given value of L 5 and 4, where the blue line is the Van Allen probes data. And this is now, okay, something very important to mention, this is now on the test set. So none of this data has been used in all the training and validation. And the purple line here is the result of the pin, which you can see agrees much better with data than the other two models I'm comparing against. Then a kind of a step forward, and I think I'm about to wrap up to leave some time for questions, is again interpretable AI, and this follows again the whole argument that Jacob made about trying to understand what is going on in these sort of black box models. So in the pipeline I just described so far, there was still this, aside from the PIN, there is this machine learning model that we use to sort of estimate future values of the LLNC, and that's makes the whole pipeline very opaque. So then we thought, okay, what if we, instead of using this black box model, we try to approximate the LLNC with a very simple model, which in our case is just a cubic interpolation. And the reason why this works well is in these two plots here on the bottom left. So again, the orange line is the median value of the LLNC on left and right as a function of L, and the black line is a cubic interpolation of that. You can see that it's a pretty good approximation. So now, if you decide to do this step, what happens is that then you can plug in the LLNC in this equation here, which becomes parameters free, and it's only a function of boundary conditions. And this is those are the results using these other two metrics I mentioned earlier on, again as a function of L, and the percentage accuracy comes with a given error bar as well. And you can see that the black lines, which are the results of when you run the forward model using this PIN derived cubic fit, this is comparable, if not better, than these other two baseline models, the Bratikon and Albert and the Ozicki et al. Parameters. Okay, I think I'm gonna skip this one, but the essence, and again there are details in the paper, is that once you have all this information, you can actually look at different values of L and see what is the relative importance of drift versus diffusion. And what we've seen is that diffusion is the most important mechanism for L, say larger than 4, but for smaller L, the two terms are actually comparable on order of magnitude. And then the last thing I wanted to mention, which I find very interesting, is that with this technique, you can run something like automatic event identification. And the reason is the following. So once you have trained your physics-informed neural network, as I mentioned, you have in your cost function these two terms. One is the mean square error with respect to the data, and the other basically is the residual of the drift diffusion equation. And then you can look into your training set at any point in space and time, and you can see how large that residual of the PDE is, which is a way of saying or assessing how well the Fokker-Planck equation works at that given space and time. In this, okay, there's a bit of normalization and color saturation, but basically what this plot shows here, these vertical red lines, these are different periods in time when that value of the residual of the PDE belongs to the sort of the 99th percentile, meaning that is very large compared to other times, which it's an indication that the Fokker-Planck equation doesn't work very well at in those given times. And then we compile this, and this again, it's all done automatically, so it's kind of automatic event identification. We compile this list of events, and then afterwards, once we have defined those start time and end time, we looked into the literature, and we actually found that for many of those events, there are a number of papers which has been published because those are associated either with CME or dropouts, or some sudden particle enhancement, so some sort of non-linear events in the sense that do not necessarily follow the Fokker-Planck equation. On the other hand, there are a small number of times when at least I couldn't find any published paper that's focused on that period, so this might still be a avenue for new discovery in using Van Allen probes data. All right, I think I'm going to conclude. So physics-informed neural network is really a game changer in general in applied math, but I believe that the best way we can use it in our problems in space physics is to solve inverse problems. And I just showed sort of a use case of how to derive diffusion and drift coefficients for radial transport for electrons in the radiation belt. You can do a number of things with PIN. You can assess when your assumption of your PDE are not valid. You can identify automatically interesting events. Something I didn't mention, you can either, if you wish, redefine electron lifetimes using the drift term, and eventually you can improve the accuracy of either nowcasting or forecasting. Crucial point is that everything we did here didn't use future KP values, because if you use future KP values, this sort of shifts the problem into predicting KP values, which is still kind of a hard problem. And okay, I'm just going to conclude with the reference here on the bottom and my email address. Feel free to send me an email to discuss any of these things. All right.
Thank you. Thank you very much, Enrico, for your talk. Very clear, right in time for a few questions. So just that you know, you had question from Misha Sitnov as you were talking, and Jacob was answering those questions in the chat. So you can see the exchange, and I think it answered what Misha was asking. Briefly, before other questions shows up maybe in the chat, let me ask you something about the PIN method and the constraint of the neural network by the diffusion equation, which is extremely seductive. Is there a limitation? Because we see that you are not using the loss term and transforming the equation. Is there an interesting limitation in this method to get something that is diffusion-like only and that cannot have source terms as in the first equation? Meaning if you knew the tau, then there will be only one D associated to
oh,
that.
Yeah, that's something we try. So you can impose a given tau, assuming that that's good enough, and then you can run the same exercise just to learn what is the DLL.
What is the D?
The tau, yeah.
Okay, that is not, okay, so that is doable. There's no constraint on the diffusion type equation. That's my question.
No. As I said, if you keep both DLL and tau, that just makes it ill-posed because they're just infinite.
Oh no, not giving DLL, giving the tau from the waves.
Yeah, I think you can do that. Yes.
Okay. Now, next question is, if you take a full form of the diffusion equation, of the Fokker-Planck equation, including acceleration, and you would write the common Fokker-Planck equation in a general way, would that be doable? Is that reachable today or not yet?
Yeah, so you're talking about doing like a 3D with cross terms and all of that. Yeah, and I believe that will be our next step. Of course, it becomes more expensive, and you will need to use more data than what we've done. But I think it's feasible from a technical perspective through, I mean, training these, the neural networks themselves, those are not huge, and the training time is really affordable. So, of course, when you go from 1D to 3D, you know, everything increases, but I think that will be our next step.
Okay. Do you think that, you know, what is the neural network methods that are for problems with time dependence so far that are coming out are the recurrent neural network models? How, and so far those recurrent models are not combined, to my understanding, with the PIN models that are based on this equation. How do you think that both can be reconciled or not, or that if we use one we can't use the other, or in order to better address the time variability and the time history and memory of the problem?
Yeah. I mean, in principle, you can define the architecture of the neural network whichever way you want. And not only that, you can also define your coefficients. You can define the input of the coefficients whichever way you want. So if you if there are strong reasons to believe that, for instance, the diffusion coefficient, it's not only time dependent, but it's also a function of past time, you can include those in the neural network as well. Yeah, again, everything makes it more complex and more costly to train, but it's definitely doable. And I believe, yeah, it's an interesting avenue to look into the future.
Last question would be on the plasma sphere. How would you see the role of the plasma density enter in the picture you just described?
Well, maybe Jacob is in a better position to answer this.
But one way I see it would be through the taus. So the taus and the wave particle interaction would enter being tied up with what the plasma sphere density is, which is a little bit what Jacob said that he was using for the waves. So, maybe I'm answering my own question, but I wanted to have your opinion about that if you had one.
Well, I mean, the way this is set up is that, again, the diffusion coefficient, and this is the sort of the heat map that I showed. I mean, the pin allows you to discover the optimal coefficients as a function of space and time. And then I believe it's sort of a second step then to understand how that variability actually depends on physical variable. I mean, time itself is sort of a dummy variable, doesn't tell us anything, right? But how electron density and other physical variables change in time, that might be a sort of a second step to understand those coefficients.
All right. So thank you very much. I'm looking at the chat. I don't see. Yes, there is a question. Sorry, just showed up from Daniel da Silva. Let's, if you can get it, but I'm going to read it. I tried using pin network for a problem in my research, and it was very difficult to train. I spoke with other pin users and found that difficult to train networks are common. Can you comment on this?
Yeah, they are difficult to train because I mean, it's that area where machine learning, there's some art that's combined with the science, and there are some sort of cookbooks to how to improve the convergence and so on. So, I mean, we can certainly speak offline to, I mean, I can only give some tips how to ease the training of the neural network.
Yeah. There's a question regarding the loss function, the cost function. Should I speak myself or ask the chat question? Yes, you can speak yourself if you are not muted. This is.
Can you hear me?
Yes, go ahead.
This is Yijun Su from Air Force Research Laboratory, and I'm very new on the machine learning, but I started learning about a year ago. But our problem is doing the computer vision. And I learned that during my exercise, the loss function is very important. And if you search loss function, you can come up with a zoo of loss function. And I just saw one of the equation, you combine two into one loss function. And basically, I need to get that at least 3 to get what I want. And I'm sure I can play around. There are so many of them. So when do we stop to play around loss function and to get it better? Because computer vision, you have an eye to judge how good they are. But for your problem, you don't have you have not only numbers. So that's my questions.
Yeah, I'm not sure I understand the question again. We can maybe speak offline more. I mean, the cost function we use, it's actually very standard, just mean square error plus the residual of the PDE. So there's really nothing fancy in the cost function.
Well, maybe that is the answer.
Maybe that is the answer.
Yeah. All right. So I'm gonna thank you, boss. Jacob had to leave for another meeting. We are past the hour by 5 minutes. We've got fantastic talk for the this RBSP seminar with you two and all the crowd attending. So thank you very much for everybody being there, for the speakers, and see you in a month for the next RBSP seminar. Thank you.
Thanks for having me. Thanks.